All right, let's see. Let's do. What?
We're good.
You good?
Yep.
Sounds like it. Let's see.
Well, maybe so.
It might be a little too good. All right. So here's an example, and the nice thing with this example, I'm going to admit to something right now. The idea of central limit theorem works no matter what, but to make a concrete example, I need you to understand, I couldn't do like every group of selecting like 15 at a time, because you start to understand how big that would get. I mean, so the idea actually allows for repetition. It's not without replacement. And you can imagine why we say with replacement, because without replacement, all the probabilities change in the middle. And that makes all the P's and Q's different, and it's just horrible, for example. So like, for example, this is I have in a hat 1, 2, 3, 4. This is a nice symmetric kind of distribution. The mean is right in the middle of all the numbers. The mean is the median. Do you guys get the answer? So I start off kind of nice. So it's going to become normal quicker than just some arbitrary distribution that's like all over the damn place. Let me stop there for a second. So 1, 2, 3, 4, nice numbers. If you picked 2, 7, 11, 38, you'll still get something similar to what we're going to get, but it's not going to be nearly as pretty. Okay, so I'll go into this admitting that I picked some pretty numbers. And of course, if I put the numbers 1, 2, 3, 4 in a hat, it's going to be a uniform distribution. 1, 2, 3, 4, they all get 1/4 of the probability. Is that cool? It's a 1 out of 4 chance you'll get any certain number. Okay, I like it. I like it. Cool. So here, if I just do this, if I just look at the original problem, the average is 2.5. That makes sense because none of them are more likely than the others. So the average will be the average is just these numbers. Is that good? Of course, if they're differently weighted, you'd have to do that. You'd have to do the whole XP of X shit, right? Here, they're all equally weighted. I don't have to do any of that shit. The mean is this. And the standard deviation is 1.118. You can calculate it the same way we did before. Are you guys decent? Okay, so you can just take my word for it. If you don't trust me, you can try to do it. I have a feeling you guys are going to go towards trusting me. Not because you trust me, but because you're like, I don't want to do all that shit. But that is the standard deviation. Okay, and does that look normal at all? I love the guys who are shaking their head yes. What's a normal curve look like? Can you do it in the air? Yeah, looks like that. It's got a bump in the middle. That ain't got no bump. It's uniform, right? So it is symmetric, so it does have some stuff going for it. It's symmetric. You know, it's nice. It starts off kind of nice, but it's nowhere near normal. It's just one freaking block. It's not a normal curve. I like it. So is everybody with what's happening? We have numbers 1, 2, 3, 4 in a hat. This represents the probabilities of each of those numbers coming out. That's amazing. So now instead of taking one number at a time, I take a number, drop it back in, take a number. So remember, when I make the new picture, I am plotting points of, bless you, the means of the samples. So how's this picture plotted? That's an individual number, individual number, individual number, individual number, right? And if I did it a billion times, I'd have 1/4 of them, or ones, roughly. You guys semi with me? A little bit? Okay. All right. So now if I take all possible samples of size 2, and now you see why I made a small collection to begin with, 1, 2, 3, 4, and I'm only taking samples of size 2, because look how big the damn thing gets after just those 2 things. So if I had a larger collection, and I was taking samples of size 3, oh my God. I'd have to print out the 11 by 17 page for you. It would suck, right? So what's going on with this picture? In white are the samples I could get. I could get 1, 1. I could get 1, 2. so forth, so on. That lists all the possible samples of size 2 that I could get. And what is it that I'm interested in? What is it that I actually want to graph? Is the means of each of those samples. Just like if I took 20 people from my alternate universe, Florida, I would plot the mean age of that group of 20 people. So I want the mean of each sample. So you can see that's the X bars. So just like up here, my sample was 1, 2, 3, 4. Down here, my sample is these numbers here. That's what I'm going to graph. Now, of course, what is there the most of? What number occurs the most in the means? 2.5 occurs the most. Right? And this is symmetric already, so we kind of expect that. It should be the most occurring thing. Okay. So the mean is still 2.5. Here's the new distribution here. And there's 16 total means. One showed up just 1 out of 16 times. You have to get 1 and 1 to get an average of 1. So it's much harder to get an average of 1 than it is to get an average of 2.5, because there's 4 ways I could do that. The mixture is what happens the most, right? Mix of lower and higher numbers. You guys semi with me? It's much harder to get a mix of the lowest numbers than it is to get a mix of high and low numbers. Okay. Like it. So this is now, when I plot this as a little histogram, does it look more normal? Hell yes, right? Is it exactly normal? Right, we're not to the point yet where we can really say, but it looks a hell of a lot more normal. If you plotted this back in chapter 2 and I said, is this normal? You would have said, yes. Starts low, goes high, then goes low again. We're a little more sophisticated now. So we know that there's supposed to be how much within one standard deviation? How much of the data should be within one step? 68%. Right, so we have other more definitive tests than just, does it start low and go high and go low again? Right? We're a little bit more sophisticated now than those days. All right? That's when we were caveman statisticians. Okay. So the mean is still, if you calculate the mean, it's still going to be 2.5. And again, you can do the whole XP of X crap. Blah, blah, blah. But I just said, here it is. This is what the mean is. And if you do the standard deviation of this, it comes out to be 0.791. 0.791 happens to be the old standard deviation divided by the square root of 2. And 2, of course, was our sample size. So that's that formula in action. So it actually happens. If you take those numbers, calculate the standard deviation, you actually get what that formula predicts you'll get. It's crazy. I like it. So again, this is a concrete example. It's still kind of like, but it is actually a concrete example of the central limit theorem happening. The mean is still the same. Mean, the standard deviation got smaller exactly the way that we said it should by that formula. All right, I like it. I don't know if you guys. Okay, this is the best kind of way to do this, is to do an actual problem. It's a little bit unsatisfactory, but you can, like I said, you can imagine if I started taking samples of size 10, you have to pass out a booklet of the results to look through. I didn't want to do that. I really didn't want to do that. Cool. I like it. Maybe. So what's the big takeaway here? The only change for a central limit theorem problem is the mean stays the same. That's not the change. The change is the standard deviation becomes this. So that symbol, what does that symbol here represent fully now? What does that symbol there represent? Standard deviation for
Groups.
that symbol is for individuals. When you divide it by the square root of n, you end up with sigma sub x bar. That's the standard deviation for groups of size n. Please let this make sense. If I'm asking what's the probability that one person makes a certain grade, I need to know how individuals are distributed so I can see where he ends up and what area is there. Just like we've been doing. If I'm talking about what's the probability that 10 people have an average grade of something, oh shit, I have to know how groups of size 10 are distributed so then I can see where this group ends up and see what area is there. Does that make sense? So you just have to use the standard deviation that's correct for the situation you're in. So I don't like teaching this way, but now that I've put you all the way through this derivation and stuff, I've said this already once, when the question gives you a sample size, you take a sample of 28 or whatever, and it asks you about the sample mean. What's the probability that the sample mean will be more than 30, whatever. Those two things tell you, oh shit, I better change the standard deviation. Because now I need the one that works for groups, not the one that works for individuals. Now if I said sample of 28, what has to be true about that problem also in the write-up? What they better say what? A sample size of 28. Can I use this chart? Definitely, for sure. Can I use the z-score for sure? Z-score chart. I like that. It said z-scart. I like that. Can I use the z-score chart? Why not? 28 is not more than 30. So the central limit theorem does not guarantee it turns normal. So in the problem, they better have said it started off normal. So if your problem starts off normal, do you need a big enough sample to make it become normal? No, it's already freaking normal. And we've already been taking one person at a time. They had to tell us it was normal, and then they take one person. I didn't need anywhere near 30 if it's already freaking normal. So if it's normal and I take 7 people, I'm fine. It's already normal. But if they don't say shit about it being normal, I better have a sample size bigger than 30. Or I can't do shit. At least not in stats 1, which is all we got. All right. So let's do, yes sir.
So for sample size bigger than 30, is that the n is bigger than 30?
Yep. What's the letter for sample size?
No.
N.
Okay. I was wondering if it meant how many people you were doing it for.
That's the same thing. Yeah.
Okay.
Yeah. So sample size is the amount of things you're actually working with, which is N.
The difference in my mind, please stop it for me, is we make groups of people, and that you're calling that a sample size as well. Is it originally a population or something?
Yes.
What we're graphing? Okay.
Yes. I like it. So originally I've got the population graphed out, and it could look like anything. That was that example of the ages in Florida, where the population looked like this. Right? Nobody was in the middle. Everybody was younger or older. Right? You guys remember that? So that was a population, and then if I take, now watch this. Now here's a part of your question that I need to address. If I say n is 5, and then I did this thing, right? We talked about the mixture is going to happen the most, so you're going to get the mean the most. And then second thing that's going to happen is a bunch of people from right there. You guys remember that? What is this that I plotted? Is this a single sample? Hell no. This is all the frickin' samples. Just like that thing here was all the frickin' samples plotted is here. So let me see. You guys, you look so weird. I understand. If I take a sample of size 73, is that sample normally distributed? No, I don't know. I have no idea if that sample is normally distributed. But would all the sample means of all samples of size 72 be normally distributed? Hell yes. Right? So here's the problem. If I take a sample of 5, let's say a sample of 72 even, and I've got, what's that going to look like now? For a sample of 72, if I plot all the sample means, it's going to look normal. It's definitely bigger than 30. Wow! What will that specific sample, where is that specific sample of 72? I don't know, maybe there. It's just one little dot in this whole picture, right? So what would this look like? Their ages, what would their ages look like? It could look like anything. I don't know. Could be a bunch of really old people, so they're over there. Could be a bunch of young people, so they're over there. But the actual, do you guys get the difference between those two things? This is a population of individuals. This is the population of all groups of size 72. So that specific listing of 72 ages, are they normally distributed? I have no idea. Do they have to be? There's no reason they have to be. I love you guys. You're all like, what the shit's going on right now? So individuals never have to be normally distributed ever. There's nothing that says individuals, when I plot them, they have to be normal. But if I plot every possible group of 72 of anything, it's going to come out to be normal enough. Any single thing I do, any single little group of things I plot each individual person, it could look like any damn thing. Okay, I like it, maybe. Now, what does what I just said have to do with any specific problems you have to do? Not much. I don't think they really ask you that question directly. And I love when I get to laugh. But they do ask, I think there is at least one question that they ask about the difference between individuals versus groups. So we'll see when you hit that. Okay. So let's do a little review of what's pertinent. And let me ask you why this kind of makes sense to study this. What are we normally working with in statistics? What are we normally working with in statistics? Groups of size, whatever, right? So if I take a group of 38 people, and I want to know if their results, and I put them on a drug, I take a group of 38 people, and I give them some experimental drug. Right? After they sign waivers and stuff. I don't just give them a drink and then say, you just got a drug. Not anymore, anyway. So a group of 38 people. I want to know how the results I get from that group, how does it compare to all groups of 38 people? That's what I want to know. And that's what this work does. That's what this does for us. I want to know if the mean time to relief of a headache. Let's say I made a new headache drug, right? I'm going to call it Jeffinol, right? Or anyway, I'm sure myself. And the mean time for relief for the regular stuff is like 20 minutes. And my group gets a mean time of 15 minutes. I need to know how their results compare to everybody, right? So every group of 30 people with the current drug, their average is 20 minutes. Now, my group got a better time, didn't they? 15 minutes instead of 20. Is that enough evidence that my drug is better than? What's missing? There's one key thing missing. Because how big is the difference of 5? Is it a big difference? What is it that tells me if that's a big difference or not? Standard deviation, thank God, right? That is the thing that helps me determine how big of a difference is that. If all my data points are an average 0.3 apart, then 5 is freaking huge. But if all my data points are 20 apart, 5 ain't nothing. So the standard deviation is that thing that helps me measure how far things are. I can't just go, yeah, it's less. Let's put a commercial together and put that shit on TV. Right? That's not good enough. I got to bring the standard. So the standard deviation for individuals is, let's say, 6.92 minutes. For the standard deviation for my groups B. Yep. 6.92 divided by? 38. Square root of 38. Which is like 1.09. Who is it?
1.12.
Alright. 1.12, whatever. It's got to go at least 3 places, remember?
1.23.
1.123? Neato. I love that shit. I wish I could say I planned that out. Obviously I didn't. So that would be, so are these far apart then? How do you tell how far apart these are? This is beautiful. I like what we're doing here. Are these very far apart then? What do you have to do? Z-score. Standard deviation tells you how big your tick marks are on your ruler. And then how do you measure distance between two things? You put your ruler down and you get a z-score. That's reading off the thing on the ruler. So z would be my data point minus the mean divided by the standard deviation. What the hell that is? It's like negative 4 point something.
Negative 4.45.
Yeah. So what do you think? From everything you know, right there, I don't even have to tell. There's going to be like ways to tell if things are far apart. We already have a way to tell. Would you say that that's very different? Is that evidence that my drug works well? Why would you say that that's very different?
So far away.
It's so freaking far away. Normally, it should be within 2 steps. And how many steps away is my results? 4.5 almost. That is significant evidence that is clinically proven to be effective in less time than the regular standard pain relief. Right? You guys, that's what that means when they say that. And of course, there's a lot of shit that could say that for that's not really meaning what it sounds like it means. But oh well. Maybe. Because maybe they got it to work 19.65 minutes. And then it comes out statistically significant difference. But is that a practically significant difference? 20 minutes versus 19.65 minutes. Would you pay like an extra $12 for that? No, right? It could be gone already if I would have just paid 12 more. Wait like 10 seconds. Oh, okay. Do you guys see what I'm saying? So sometimes it's clinically proven to be more effective. Yeah, by this much, I'm going to pay 10 more bucks for your shit. No. That's the thing that people don't see. Okay. So this is basically, we're getting to the point in the semester when we've got a lot of these tools we've been working on. And I know it's been a lot of nuts and bolts stuff so far because there's a lot of freaking nuts and bolts we got to get laid down if we're going to start looking at a problem the way we just did. This is going to be chapter, I can't remember the chapter, the hypothesis chapters. I think it's chapter 9 when they started the hypothesis tests. Yeah. So hypothesis tests are going to be, can you test a claim that somebody's made? So they claim that this class improves your SAT score by 300 points. So we take a sample of 73 people, they take the class, and we see what the results are, and we see, is it statistically significantly different from what the average person did? Do you see that we're getting to that point where we can do that kind of thing? Because we've laid a lot of groundwork. A lot. You've been here for the whole damn thing, so you're like, yeah, we've been doing a lot of shit. Okay. Let's reel it back in, Jeff. Let's do a specific problem here. Let's see. Mean. Golf score. Is that a normal golf score for like a rounded golfer, pro golfer? Okay, good. I love it. Nobody knows golf? Sweet. And if you don't golf, just be quiet. It's another 64 with. But this is for a certain course somewhere, right? For a certain golf course somewhere. Another 64 with the standard deviation of, let's say 8.1. Okay. We take a sample of 42 golfers. A, why can we use the z-score chart? To answer probability questions. You know, I'm going to ask, find the probability that the group of 42 gets an average. Blah, blah, blah. Why are we allowed to use the z-score chart for areas in this problem? Yeah. So n is 42, it's greater than 30. So as long as I'm asking questions about the sample mean of the 42 golfers, then the distribution of all groups of 42 golfers is known to be normally distributed because it's more than 30. Okay, I like it. So B, find the probability that the sample mean of the 42 golfers is less than 60. So do that. Take a minute, try to do that. Sorry if you gave me your calculator back. I should have held on to that sucker. Random freaky noises.
I don't think so.
All right. What's the mean I'm going to use for the sample means? I'm going to put it right in the middle of my picture. Yeah, because the mean doesn't change. Just because I'm taking groups of 42 golfers doesn't mean the average of all the golfers is going to change. It's the same golfers. I'm just taking 42 at a time. So it's still 64 of a mean. That's related to that statement, mu sub x bar equals mu. The mean doesn't change. But what definitely changes is the standard deviation. The thing gets skinnier. Everything rushes to the middle. What does standard deviation become?
1.251.
1251?
1.251.
It's not that I don't trust you, it's just better to get the crowd to agree. Okay, so now it's going to be just like any other standard Z-score problem, right? I got to put on there the number I'm interested in, 60. Shade in the area that I want, less than, sweet. And then I make a Z-score. Now some people would say the Z-score formula has changed. You know me, I would say, no, it hasn't changed, we're shit. But to show you what the Z-score formula looks like now, our data point is actually going to be a sample mean. So it used to be this. Now it's the same damn thing, but it looks like this. the sample mean minus the mean of all the sample means divided by the spread of all the sample means. It's the same stupid formula. It's the data point I'm curious about minus the middle divided by the spread. It's pretty cool. I mean, the mean doesn't change. Right? Now I'm asking questions about a mean of a group, not just individuals. And my spread, I can't use this spread number because that's for individuals. I have to use the one that works for groups. Okay. Right. So what do I get here? Z equals, my data point is 60 minus 64 divided by the new standard deviation. Yeah. Negative 3.3 almost?
3.2.
3.2.
Exactly.
3.2?
It rounds up.
So it's like 3.198.
Yeah.
All right, so negative 3.20. I like it. So I really desperately want you guys to see. This is why that kind of, a z-score problem by itself has to be easy. I give you a raw score with the mean and the standard deviation. You make it into a z-score and you look it up on the chart. And you adjust it if you have to. You subtract it from 1, whatever. That should be easy. This, I take a sample, I ask about the sample mean. What's the only thing that changes in that whole kind of recipe is I have to use a different number on the bottom. I like it. So when you look at negative 3.2, what do you get? 0.0007. 0007. I like it. Okay, I like it. Okay. Let me ask you a couple of questions that get us ready for something coming. Because I mean, I could ask you some more questions, but you realize you've already done what you need to do? You got the new standard deviation. So if I said find the probability X bar is greater than 70, you make a z-score, you look it up, you do 1 minus that area, and now it's just the normal problem. You like it? People... see, let's do another one. Let's do another one and I'll show you how I like to set up a part A and part B. And then we'll do the freaky thing that's leading us to the next stuff. I really want to make sure you guys understand. The whole thing about alternate universe Florida, the whole thing about that sheet with all the colors on it, it's all trying to explain why the mean doesn't change and the standard deviation does, right? But alternate universe Florida was a very conceptual discussion. I didn't actually go to alternate universe Florida. I wish I could. I don't have such a portable one. I don't. The paper with the colors is a very specific example of what happens when you take samples of size 2 in this case. But I really like to show you it's uniform and then it suddenly becomes a pyramid thing and it looks a lot more normal. It's really kind of, and I only took a sample size 2 because it started off kind of nice. So 30 is the magic number for like anything. If it starts off nice, maybe you only need 10 for it to come normally now. You guys see what I'm saying? For us, it's always got to be 30. We don't know, we're not sophisticated enough to know exactly what number for certain conditions. We'll just say it's always got to be more than 30. Let's see. No, I don't want to do that. Tomato diameters. Like a certain type of tomato are known to be normally distributed. So right there, how big of a sample do I need to be able to use the chart?
30.
Doesn't matter because I already told you it's normal, right? I don't need to save this guy's ass by a large enough sample size because his problem is like, I got it. I'm already normal. Right. So I can take 2, 3, I can take 1, just like we were doing before. So tomato diameters are known to be normally distributed. All right, let's say the mean of all of them is, let's see, let's say 4 centimeters with a standard deviation of 1.209 centimeters. I like it. Love it. You guys are like,
Go on.
we picked 1 tomato. Find the probability that its diameter is more than 6. A nice big old tomato. This is no ordinary tomato. This is a cherry tomato. If you don't know that line, it's too bad. We pick 1 tomato to find the probability that the diameter of that tomato is more than 6. So why? Again, just to make sure you guys get it. Why am I not concerned this is not greater than 30? Because it already says it's normal. So I like to give you a mixture. I like to give you a problem where you don't say shit. So you got to check and make sure that it's greater than 30. I like to give you this kind of problem because you'll see in a minute why. So how do I write this in, like in this notation? Yeah, x greater than 6. So try to do that problem. That's an old z-score problem. You don't have to change anything, right? You can even say n is 1. So sigma divided by square root of 1 is there's sigma. So the standard deviation doesn't change. So this is old news. You guys might be like, I ain't in that homework yet. Ain't old news to me yet. All right, step it up. So how do I make a z-score? It's going to be, what's the formula going to look like? 6 minus 4 divided by 1.209. 1.64? 654. Neato. 1.65. Always two places because the little chart that Crazy Jeff has is used goes to two places. So when you look at 1.65, obviously it's not going to be the answer. Right? 'Cause whenever you look up a z-score, you get the area below something. So what do you get when you look up 1.65?
0.9505.
9505. So my actual answer is going to be
0.0495.
0495. I love it. So about a 5% chance, if I pick a tomato out of this group, I'm going to get one that's got a diameter more than 6 centimeters. All right. So now, what if I take, we pick 7 tomatoes. You can even spell it like this if you want to. Tomatoes. Pick 7 meters. What's the probability that the sample mean of those 7 tomatoes is more than 6? Now, should this be a bigger or smaller number than that? Why?
It's already really low for the individual.
Yeah. To be honest, it's not quite good enough because I could actually ask a question about really close to this and it's going to increase. So everything's going to go towards the middle. So there's going to be less stuff left out here in the tail. Right? I like it. So that's why this is going to be less than that. I like it. So now the very first thing I've got to do is what? Yeah, I need what I call my new standard deviation. Sigma sub x bar is going to be the old standard deviation divided by square root of 7. .48. I don't know. Making shit up.
457.
What is it? 0.46? 0.457?
Yeah.
457. Is everybody with me here so far? Again, what is it that made me realize I had to do this? Took a sample, asked a question about the sample mean. Then I know, oh shit, essential limit theorem, you don't even have to think that. Oh shit, that thing where I got to change standard deviation. And then I do all the same exact work, but right here instead of 1.209, I got 0.457. So now the z-score, same picture, same everything. The z-score, though, is going to be 6 minus 4 divided by 0.457. It's going to be like 4 point. Who is it?
4.3.
Really? I was going to say 4.4. That's pretty good. 4.38. Now, I don't think we talked about this occurrence much. I might have mentioned it really quickly. Try to use your chart to tell me what that area is. Yeah, so the area below 4.38 is what's it say? 9999?
Yeah.
Now, of course, they just say at 3.5 forever after it's 0.99. That is BS, right? I mean, the further you go, the less shit's going to be above you, the more shit's going to be below you. It doesn't just suddenly go, let's just stay at 0.999. Does that make sense? So if you use what the chart says, I won't, that's beautiful, that's great. Technically though, what's below here is approximately 1, so what's above here is approximately 0. Should make sense. If the mean is 4 centimeters, and that's the spread, and I'm trying to get 7 that I randomly pick that have more than 6, that's basically impossible. I ain't gonna happen. I have to be really specific and pick this one and pick this one. Well, I'll pick this, right? Because there's no way I just randomly pick and go, oh wow, it came out more than 6 when it was supposed to be near 4. Ooh. So this answer makes sense. Now that does not mean it's impossible. right? It just means it's really, really unlikely. Now, if you say 0.999 and you say and your answer is 0.0001, that's fine. I'll take it. That's fine. That's your chart's way of saying really unlikely. Does that make sense, that distinction there? If you get out to freaking 8, a z-score of 8, it ain't 0.0001. It's like 0.000000. It's crazy. Okay, I like it maybe. Oh, all right. Let me talk about, there's two little things I want to do, and then we'll get out of here a little early. Any questions on this here before I take it down? Is that better? Okay. Yes?
How high does the z-score go up?
Well, on the chart,
3.5.
yeah, in theory it goes to infinity. Yeah. This picture, theoretically, this picture goes from negative infinity to infinity. In fact, you're going to hate your asses because now you've unleashed the math geek in me. But have any of you guys heard of Zeno's paradox?
That some infinities are bigger than other infinities.
Sort of related to that idea. All right, Zeno's paradox. You're like, is this going to be on the test? I don't give a shit. Zeno's paradox. The first time I heard this, I was like, what the hell? Zeno's in city A, and he wants to go to city B, but he's never going to make it there because he's got to travel halfway, and then he's got to travel half the distance left, and then he's got to travel half the distance left, and then he's got to travel half the distance left. Right? And smart ass me, I told my teacher when he first told us that, I said, well, just tell him it's twice as far to the city than it really is. I got to travel half, well, I'm here. Paradox solved. So here, this is eternally getting closer and closer and closer. It's always getting closer, it just never gets there. And of course that's called what do you guys, does anybody know? Asymptotic. Yeah, that's asymptotic. Now in reality, for like fish lengths or something, when I get to a 0 fish length, it ain't going past that. You haven't got these anti-fish, right? -4 length fish. If it comes in contact with a fish, it's going to explode. No. I love some of you guys looking at me like, anti-fish? What the shit's going on? All right, I'll stop with that. You got some more examples here. Learning stats, Zeno and exploding fish. All right. There are a few problems in the homework, and I like to ask this kind of question also. But let me give you two things here. Let me say the mean. Let's say the mean is 20. Standard deviation of 1.7. And I want to know, and I'll tell you, it's normally distributed. Jeff, either normally or normal, not in the between. Right? So between what two raw scores would we find 90, let's do 95% of the data. You got to be careful. You can't go to empirical rule anymore. We'll be a lot more precise now. So this is related to the question, find the z-scores bounding the middle 40%, for example. Right? There's a problem in the homework like that. So I'm trying to look around and see who's hit that problem. Not a lot of people yet. Okay, I got you. Between what two raw scores will we find 95% of the data, or more specifically, bounding the middle 95%? If I say it that way, it's a little bit clearer how to draw this. So I want bounding the middle 95%. So I want like here. Bounding the middle 95%. So the chunk in the middle is 95% of the data. So how much data am I leaving off? 5% total, right? How much on just that one side? 2.5%. Now why would I go down that road I just did with the numbers? Because what's the first step to try to work my way back to the raw scores, the x's? I know areas. What do I then have to find? Z-scores, because then I can use my backwards formula to get the raw score. I like it. So, how do I find the Z-score, for example, this one? What area am I going to look up? Yeah, 0.025, like we just said, there's 2.5% on either side. Now what's interesting about this is, if this was negative 1.8, this is going to be positive 1.8 because of symmetry. It bounds the middle 95%, so and it's symmetric around 0. That's beautiful. I don't have to do twice the work. Right, so if we look at 0.025,
Negative 0.196 this way.
yeah, negative 1.96. So that's negative 1.96, which kind of gets close to empirical rule. What's empirical rule say? When you go out 2 steps, you catch 95%. So that's roughly 2 steps, right? So empirical rule is just kind of rounded a little bit. Make it easier to remember. All right, let me stop here for a second. Is everybody cool with what I've done so far? Yes?
Where'd you get the 1.96?
So if you look at 0.025 in the chart, in the body, this is not a z-score, this is an area, so that's got to be in the middle. And then you can look out to see the z-score. Now, how do I change these? Now, I've got between what? 2 raw scores. So I've got to change both of these into raw scores. And of course, the formula for that is do you guys see how it's sort of well, anyway, let me let you guys try this out. So I got to do the mean plus 1.96 times this, and the mean minus 1.96 times this, and that's going to tell me the 2 raw scores that it fits between, the 95% of the data. I like the half here, just sort of waiting. Somebody's gonna